Greetings to all in Dr. Abha Chemistry Pathshala. So let us move ahead with our journey of aldehyde, ketones and carboxylic acid. In your textbook, the methods of preparation of aldehydes and ketones, they are together. In this video, I'm going to take only methods of preparation of aldehyde, aliphatic aldehyde as well as aromatic aldehyde. So let us dive straight onto the screen for methods of preparation of aldehydes. Methods of preparation of aldehyde. Aldehydes and ketones, they are known as carbonyls, and the methods of preparation of aldehydes and ketones are pretty similar. So in this lecture, I'm going to take up the methods of preparation of aldehydes, but at the same time, I will be talking about some of the methods which are identical for ketones as well. I'm categorizing the entire method of preparation into three parts: aliphatic. In aliphatic, we will be talking about methods of preparation of open chain aldehydes like acetaldehyde, butyraldehyde, propanaldehyde, right, or cyclohexane carbaldehyde, that is, which are not aromatic. Secondly, aromatic, that is benzaldehyde exclusively, and the third method which will include the common methods which are applicable on both. Among these three methods, there are 50% of the methods which are common for ketones as well. So as we move towards each and every category, I'll keep telling you which methods are applicable for both. So let us get started for the first category, aliphatic aldehyde. The first method will be, we can perform hydration of alkynes. This is for aldehydes and ketones both. For aldehyde, we take acetylene, or what we call as ethine. We just add it into water in presence of mercuric salt, HgSO4, and small drops of H2SO4. Hydration takes place, water is added to the alkynes, and simply the double bond remains, triple bond breaks, double bond remains, and you have H added on one side and OH added on one other side. If you look at this structure has got ethanol. That is, on the same carbon you have OH and double bond. Look at the circled carbon, it has got a double bond and it has got an alcohol. So this will undergo tautomerization. Such system undergoes tautomerization, and in tautomerization H will get transferred. H gets transferred. So instead of CH2, now we will have CH3, and here we will have a double bond O, because H has got, which H gets transferred, guys? The H which I am highlighting with green in a circle, this H gets transferred to the vicinal carbon and you get carbonyls. So here you get acetaldehyde. But if you take higher alkynes, you will get ketones. Let's move on to the second method. If you take alcohols and you selectively oxidize them, you will get aldehyde. Again, if you take 2-degree alcohol using the same reagents, you will get ketones. For example, if you have this 2nd-degree alcohol and on selective oxidation, you will have ketone, right? Now, what are the oxidizing agent which do such selective oxidation? So what you can use is, you can use PCC, that is pyridium chlorochromate, CrO3 in anhydrous medium. If you take CrO3 in acidic medium, it will give you directly acid. In acidic medium, you will get acid, but in anhydrous medium, you get carbonyls. That is, for 1 degree, you get aldehyde, for 2-degree alcohol, you get ketone. From gem dihalides, on this halide, if you perform substitution reaction, passing aqueous KOH, so on both the halides, there will be OH, which will finally give out water to give you CHO. If you want, you can show the intermediate step like this. Although this step will be highly unstable, you will have OH on the same carbon which will give you water to give this product. From only benzaldehyde, we first use benzene. The reaction is known as Gatterman-Koch reaction. Here we take benzene and we perform electrophilic substitution of benzene with the help of CO and HCl. And we take anhydrous AlCl3, which helps in electrophilic substitution. It helps in electrophile generator, or we can take cuprous chloride, right? So what happens is CO and HCl will give you HCOCl, from where we are able to generate HCO plus as an electrophile. So this HCO gets substituted on the benzene ring and the byproducts are HCl. So this method is for benzaldehyde. It's a kind of electrophilic substitution. We also call it formylation because formyl group is added on the benzene ring. Formyl has got something to do with CHO. Next method, side chain halogenation. In side chain halogenation, we take toluene, then 2 hydrogen replaced by 2 chlorine atoms by free radical halogenation. When we perform hydrolysis, now what will happen at hydrolysis, that both these chlorine will get replaced by OH, and when on the same carbon we have 2 OH, I have already said what we get is water comes out and we get C double bond O. So exactly the same thing happens here, and you have 2 OHs which will remove water to give you double bond O, that is aldehyde, right. So this is side chain halogenation. If you want, you can also get COOH by this method by side chain halogenation, although directly oxidizing toluene will also give you benzoic acid, right. We cannot prepare ketone via this method. No ketones can be prepared via this method. Let us move to the next one, Etard's method. So it is toluene, and this toluene is reacted with chromyl oxychloride gas. We remind you, you get the same gas when you try and do the qualitative analysis of chloride ion, right, chromyl chloride test, and you take CS2 as a medium, and what actually happens is, so 1 hydrogen remains intact and 2 hydrogens, they are replaced by OCr, OH, Cl2, and this is a bulky group, so only 2 places gets displaced. And when you perform hydrolysis, simple hydrolysis you do in presence of some drops of acids. So this is acidic hydrolysis. What happens is, on the benzene ring, this one H will remain intact and both these groups will be displaced by OH, which will give nothing but C double bond O. So straight away I am making it C double bond, and you get byproduct of chromyl salt and oxide, right. If you want to balance the reaction, you will have 2 of this and 1 of this, right. So this is your Etard's method, and there is one more reaction which is very similar to Etard's. Again we take toluene, and here what we do is we take acetic anhydride of chromic oxide, and the complex what we get, again we will get, at one position you will have hydrogen only and you get a acetate group on 2 positions. Now guys, this group is so big that having it at 3 positions will cause steric factors, that is why we are only having it at 2 places. And now what we do is, by simply performing hydrolysis as we did in the previous methods, we will replace both the acetate groups by OH groups, and you know that 2 OH groups are never stable, so they remove water to give you what I write here, and you get acetic acid as byproduct. Now we move on to the third category, that is methods for both aliphatic as well as aromatic. So the first category is from nitriles, and this is only for aldehyde, not for ketone, only for aldehyde. So if we have RCN or we have an ester in presence of diol, H followed by hydrolysis, we directly get aldehyde. Now diol H is unable to make any difference on double bond, but esters and nitrile, it will convert this acid part directly to aldehyde and CN part also to aldehyde, and here we get C2H5OH as byproducts because this alcohol part remains unaffected, but this acid part CO gets oxidized to, sorry, the acid part gets reduced to aldehyde. Now diol is aluminium diisobutyl. So this is your isobutyl, yeah, this is your isobutyl. So we have two such isobutyl groups, and this is hydride. So diisobutyl hydride, this is your diol H. Second, again from nitriles, Stephens reaction. In Stephens, you take nitrile, you can take aliphatic or you can take aromatic nitriles reacted with a reducing agent SnCl2 plus HCl, right? And it first partially gets reduced to an imine, and this imine, when hydrolyzed with acidic hydrolysis, will give RCHO, NH3. Similarly, same here, you can use same SnCl2 plus HCl. This will be the first step, and the second step is going to be acidic hydrolysis, and what you'll end up is benzaldehyde. We cannot prepare ketone by this method. This is only for aldehyde. Let's move on to the third method. Third method is for both aldehydes and ketone, and it's a very important reaction from grade 11. Many of you would remember this reaction with by the name of that Hutt formation, ozonolysis, right? So ozonolysis is addition of ozone across the unsaturation, right? So I will just take double bond, yeah. So what if I take on one side and I take alkyl on the other side? So once I perform ozonolysis, for this you can go through that video of ozonolysis. This method you get combination of aldehyde and ketone if carbon to which the double bond is added. So here I have taken the example where you are getting an aldehyde, aliphatic and aromatic aldehyde, that is benzaldehyde. But what if about this was having no hydrogen, this carbon was having no hydrogen, and this side you have the same diagram, you have benzene, right? So in this case, for the same reagents, that is ozone followed by Zn and H2O, you would have landed up with a ketone as well plus benzaldehyde. So this reaction is a very good reaction to prepare mixture of aldehydes and ketones, or you can get the same aldehyde also depending upon what alkene have you taken. So these were the important reactions for the preparation of aldehyde, and some of the reactions are applicable for the preparation of ketones as well. One more method for the preparation of aliphatic as well as aromatic aldehyde. We take acid halide, that is either benzoyl halide, or we can take alkyl also, and we partially reduce its with H2 in presence of PD, palladium, which acts as a catalyst, and BaSO4, which acts as a poison. Now, the function of this poison is it ensures that the reduction is only stopped at aldehyde. That is, we get an aldehyde here and we get HCl, but we do not get, otherwise if we take H2 and PD, there is a likelihood that we may go till alcohol. So, this poison ensures that we stopped at aldehyde, and the reaction is a very famous reaction known as Rosenmund reduction. So, these are the methods of preparation of aldehydes, aldehyde.